We previously studied Thevenin theorem with independent sources. In this video, we will study Thevenin theorem including dependent sources. To explain how to calculate Thevenin voltage and Thevenin resistance in a circuit that involves dependent sources, we will consider the following circuit. So let's say we have these two sources and a few resistors, and these are our terminals A and B. The resistors are 1 ohm, 4 ohm, 2 ohm. Let's say this one is also 1 ohm. The dependent voltage source, so this is the symbol for a dependent voltage source. And the value of this source is 3 VA, where VA is defined as the voltage across the 2 ohm resistor. And the polarity is as shown. The current source is producing a current of 4 ampere that is flowing upwards. So this is our circuit, which involves one dependent voltage source, and the voltage of this source depend on the voltage across the 2 ohm resistor. And we have an independent source which produces 4 ampere. So the current produced by this source is independent of anything. It will always produce 4 ampere. So therefore, this is an independent source, whereas this voltage source will produce a voltage which will be dependent on the voltage across this 2 ohm resistor. If this voltage increases, then the output of this voltage source will also increase, and therefore this is called a dependent voltage source. So the first task is to find the Thevenin voltage. Just to remind you, we want to create a circuit which will be equivalent to this circuit, and that circuit will have a single voltage source and a single resistance, and the resistance is RTH, and the voltage source value is VTH. So this is the equivalent circuit, which is called the Thevenin equivalent circuit, and we want to find these two values, VTH and RTH, so we can create this equivalent circuit that will represent our original circuit, which is supposed to be complex compared to this one. So we want to find VTH and RTH. So the first thing we will do is to find VTH, and we know that VTH is equal to the open circuit voltage of our original circuit. So the terminals A and B, we will keep it open. And in this situation, we will find the voltage that is produced over here. So this is called the open circuit voltage. And this open circuit voltage is our Thevenin voltage. To find VTH, I will solve this circuit using nodal analysis. For nodal analysis, please watch my previous video on nodal analysis. So to apply nodal analysis, I will choose a reference node, which is over here. That's our 0 volt. And I will find the other nodes at which we need to find the voltage. So in this circuit, I can see that I have only one node, which is over here, V1. We can also consider V2, a node over here, but this doesn't really give us any more information because the output is open, so the current in this branch is equal to 0. So therefore, this doesn't seem to be a node because the current that is coming in this branch goes out in this branch. So it's kind of series, two resistors in series. So therefore, we do not need to consider this as a separate node. Although if we do, we will get the correct answer as well, but that will not provide us any more information that we need. V1 is sufficient to solve for the Thevenin voltage. So let's consider this circuit with only one node, V1, and we will apply KCL at node 1. So KCL at node 1. If we apply KCL at node 1, it says that the current entering, so the current in to the node is equal to the current out of the node. The current that is entering this node is, let's say, one is this current, which is entering the node. The other one is the 4 ampere current, which is coming into this node. And the third current is this one, which is leaving the node. So we have these three currents, and we can just write KCL and then represent them in terms of the voltages. So the current that is entering the node, let's consider this current. The voltage at this point is 3 VA because of this source. you see we have 0 volts over here, and this source will produce 3 VA, which will give us 3 VA voltage over here. And on the other side of this resistor, the voltage is V1, and the current flows from higher voltage to lower voltage. So the current that is entering V1 node is 3 VA minus V1 divided by the resistance value. So this is the current that is entering from this branch. Similarly, the current 4 ampere that is entering, that's a constant current, and therefore we can just simply write 4. This is also the current that is entering the node, and the sum of these two should be equal to the current that is leaving the node, and the current leaving the node is V1. So we can say V1 minus V2 if I assume 2 nodes, but I don't want to do that because that will just unnecessarily increase our work. So I will say it's V1 minus 0 divided by the resistance in the branch, and the resistance is 6 ohm, which is 4 ohm plus 2 ohms. So I can say V1 minus 0 divided by 6 ohms. So you see, this is how we can avoid unnecessary nodes V2 over here. So the current that is leaving is now V1 divided by 6. All right, so this is our equation. Now let me try to simplify it a little bit. So we will multiply by 6 on both sides. So that will give me 6 times 3, 18 VA minus 6 V1 plus 24 equals to V1. All right, and now I can simplify it further. So I will have 18 VA minus 7 V1 plus 24 equals 0. All right, so this is our equation that we obtained from node 1. And because we have only one node, therefore we will get one equation, and we should be able to find the voltage V1 from that equation. However, here we are seeing that we have another variable, which is VA. So you see, V1 is the variable that is unknown, so we need to find V1. But in this equation, we have another variable, VA. And VA is also at this point not known to us. So therefore, the problem in this equation is that I have two unknowns and I have only one equation. So we need to find VA first. And VA is given over here. So how can I find VA from the circuit? So you can see that V1 is actually going to be divided between these two resistors, 4 ohm resistor and 2 ohm resistor. So some of the voltage will be dropped across the 4 ohm and the rest will be dropped across the 2 ohm. And you see that the voltage across the 4 ohm would be twice as much as the voltage across the 2 ohms, because 4 ohm is twice as large as 2 ohms. As an example, if we say that, let's say V1 is 6 volts, so then 4 volts will drop across the 4 ohm and 2 volts will drop across the 2 ohm resistor. However, we do not know what VA is, so we will apply VDR and just write what will be the voltage across the 2 ohm resistor. So here, if I apply VDR, I will say that the voltage across the 2 ohm resistor, which is VA, should be equal to the voltage V1 times the resistance across which I want to find the voltage, so that's 2 ohm in this case, so 2 divided by the total resistance, which is the series sum of the two, so it's 4 plus 2, so that's 6. So 2 by 6. So therefore, we can say that VA is 1 by 3 V1. Okay, so, or V1 divided by 3. So now I have VA written in terms of V1, and now we can put it over here to get rid of the term VA. So therefore, I will have 18 VA, which is V1 divided by 3 minus 7 V1 equals to negative 24. And now 3 times 6 is 18. So I will have 6 V1 minus 7 V1 equals to negative 24. Or we can have negative V1 equals to negative 24 multiplied by minus 1. So therefore, V1 is 24 volts. So we got V1, the voltage at the node 1, and that is equal to 24 volts. All right, so now that we know this voltage, we can now easily find the voltage across the 2 ohm resistor. And the reason why I need to do this, because I want to find the open circuit voltage. And the open circuit voltage will be equal to this voltage, VA, because the current in this branch is 0, because it's an open circuit. So if the current in this branch is 0, we will have a 0 volt drop over here. So therefore, whatever voltage we have here will be the same as here at point A. So therefore, we are trying to find VA. All right, so using the same VDR, here, we can now see that how much VA will be, because V1 is 24 volts. So therefore, VA will be equal to 24 times 2 divided by 6, which is equal to 4 times 2, and that is 8 volts. So we found that VA should be 8 volts, and now I know that from this point to this point we have 8 volts drop, and there is 0 volt drop from here to here, so that's 0 volt, and therefore V open circuit is also 8 volt. So VTH, which is equal to the V open circuit, is 8 volts. So we did the first half of the problem. We got the Thevenin's voltage. The next task is to find the Thevenin resistance. So I have redrawn the circuit over here to find RTH. And to find RTH, we need to turn off all the sources. We need to remember that we will turn off only the independent sources. We cannot turn off the dependent sources because they depend on the voltages in the rest of the circuit or the currents in the rest of the circuit. So those sources depend on other variables in the circuit, so therefore we cannot turn off those voltage sources. So if I turn off the independent source, which is the current source in this case, my circuit will look something like this. I will have one independent source, then this branch will be open. Our terminals A and B. So you see, the current source that was here originally, we had to replace it with an open circuit, because to turn off a current source, we have to make sure that the current is 0. And to make the current 0, I have to just open that branch. So therefore, we do not have this current source over here. Now we have a 1 ohm resistor here and a 4 ohm resistor. This one was 2 ohm and this one was 1 ohm. Now this is our circuit, and we want to find, this is 3VA. Now this is our circuit, and we want to find the input resistance, Rin. So the resistance that I will see if I connect, let's say, a multimeter between these 2 points A and B. So I need to find out the equivalent resistance of this entire circuit. If we have only resistors, then it is very easy to do. However, we have a dependent source here, and therefore it is not possible for us to use the methods that we used in the past, which were series and parallel combinations of resistors. So therefore, we need to come up with a different strategy. And the strategy is that we will apply a voltage over here. We will apply, let's say, a convenient voltage, and we can choose any value that we like. I will apply, let's say, 1 volt. So we will apply a voltage of 1 volt. And then we will see how much current I is produced. Based on this current, we can find the resistance of the entire circuit. Now you see, you can think of is that your terminals are A and B, and to the left of your circuit is an equivalent resistance, that is Rin. That's your resistance of the circuit. So your circuit can be represented with this single resistor. And now we have applied a 1 volt source. And because of this source, a current will flow, I, and because we know the voltage and the current, so therefore we can find this resistance Rin. All right. So that's the plan. We are going to apply a voltage source, measure the current, or calculate the current, and based on these two values, I can calculate Rin, and you can see that Rin will be equal to the voltage drop across Rin, which is 1 volt, divided by the current I. So this way we can find Rin. It is not necessary to use a voltage source. We can also use a current source over here. So if I use a current source of, let's say, 1 ampere, then I will measure the voltage that is produced from point A to point B, and that voltage, and using the 1 ampere current, we can then calculate the resistance Rin using Ohm's law, just like we are doing using a voltage source. So the choice is up to us. We can use either a voltage source or a current source. In this case, I'm using a 1 volt voltage source. Now the objective is to calculate the current I. This is the current I that we need to calculate so that we can calculate Rin. To do so, I can either use nodal analysis or I can use mesh. So in this case, I will use mesh analysis, and I will assume that I have two meshes. The current in mesh 1 is I1, and the current in mesh 2 is I2. We have discussed mesh analysis in a previous video, so if you have not seen that yet, I would recommend to watch that video. Now let's apply KVL to mesh 1. So KVL in mesh 1, KVL says that the voltage rise should be equal to the voltage drop in a single mesh. I will go clockwise in the mesh 1, and I will start from this point A. When I go clockwise, I see a voltage rise because I go from point A to point B, and this source is actually increasing the voltage. So the voltage at B is higher than A, therefore this is a voltage rise. So I see a voltage rise of 3 VA. Then I see a voltage drop over here, and I see a voltage drop over here. And these two resistors are connected in series, and the same current I1 flows through them. So I can combine them in one resistor and say this is a resistor of 5 ohms. So I have a current I1 flowing in a resistor of 5 ohms, and that will cause a voltage drop of 5 I1. And then we have another voltage drop of VA. So that is VA. Now simplify it a little further. We have 2 VA equals to 5 I1. Now remember, when we are solving mesh equations, we want the equations to be in terms of the currents I1 and I2, because these are the variables that we want to solve for. And if we have two equations, then we have two variables over here, and we can calculate I1 and I2. However, in this equation, I have something called VA, which is, again, an unknown, but we want to write it in terms of I1 and I2. And looking at the circuit over here, the current in the 2 ohm resistor, there are two currents, I1 flowing downward, I2 flowing upward. The polarity of VA tells me that I1 must be larger than I2. That's why the voltage is higher on the top and lower on the bottom, because the current flows from higher voltage to lower voltage. So therefore, the voltage drop VA across the 2 ohm resistor, according to Ohm's law, will be equal to, so VA is equal to 2 ohm resistance times the current through it, so I1 minus I2. So the sign is important here, I1 minus I2, because I1 is the larger current. So therefore, this difference will be positive if I choose I1 minus I2. And that will give me VA in this polarity, that plus above and negative on the bottom, because the net current is flowing downwards if I1 is larger than I2. So this is our VA. Now let us put VA in this equation over here. So I will have 2 times 2 will be 4 I1 minus 4 I2 equals 5 I1, which means I will have negative I1 minus 4 I2 equals to 0. Or we can say that I1 plus 4 I2 equals 0. We can leave it here, or we can say I1 is negative 4 I2. So this is our first equation that we got from the first mesh. Now let's apply KVL to the second mesh. In the second mesh, again, I will choose a starting point, and let's say this is my starting point, which is point C, and I will go clockwise, and I will see where is the voltage rise and where is the voltage drop. Going from C upward, I see this is a voltage rise, which is equal to VA, and then there is a voltage drop across the 1 ohm resistor, and then there is a voltage drop because of the 1 volt power supply, the voltage supply, and that's about it. We have these three terms only. So therefore, KVL in mesh 2 gives me that rise should be equal to drop. And remember, these are voltage rise and voltage drop. So going from C all around this loop, I see a voltage rise of VA. So the voltage rise is VA. And then I have a voltage drop of 1 ohm times I2, because the current in the second mesh is I2. So the current times the resistance is the voltage, and that's a voltage drop because we are going from positive to negative. We are going from higher to lower voltage, so that's a drop. Similarly, when I go from this point to this point, I'm going from a higher voltage to a lower voltage. So that's a 1 volt drop. So therefore, I will have 1 volt drop over here. Now VA, we already found that VA is 2I1 minus I2. So this is 2I1 minus 2I2 equals to I2 plus 1. And now we can say that 2I1 minus 3I2 equals to 1. This would be my second equation. Now I can use the first equation where I1 is negative 4I2. So I will have 2 times negative 4I2, negative 3I2 equals to 1. And 4 times 2 is 8, so I have negative 8I2, 3I2 equals to 1. This is negative 11I2 equals to 1. And this tells me that I2 is negative 1 over 11 ampere. So we calculated I2. I2 is negative 1 over 11 ampere. Now you see, I2 is flowing in a clockwise direction. But we are not interested in I2. We want to find this current I. And you can see that the current I has the same magnitude as I2, but the opposite direction, correct? Because I2 is flowing clockwise, whereas I is flowing counterclockwise. So I is equal to I2, but opposite direction. So therefore, I is negative I2, which means it is 1 over 11 ampere. So now we have found that when we apply a 1 volt at the terminals A and B of our circuit, the current that flows in the circuit is 1 over 11 ampere. So let me draw it here. So I applied a 1 volt to my circuit. Let's say this was our circuit, which is a black box, whatever circuit we had here. But we found that when I apply 1 volt, it produced a current of 1 over 11 ampere. So therefore, the input resistance of this circuit is V divided by I, which is 1 divided by 1 over 11, which is 11 ohms. So Rin is 11 ohms, and Rin is the Thevenin's resistance. So Thevenin resistance is also 11 ohms. So we have calculated the Thevenin voltage and the Thevenin resistance for a circuit that had a dependent source. Now our Thevenin equivalent circuit would look something like this. We have 11 ohms, and the Thevenin voltage was, I believe it was 8 volts. Let's see, Thevenin voltage we found somewhere here. So this is the Thevenin voltage. We found it to be 8 volts. All right, so this completes the analysis of the Thevenin equivalent circuit, but we just want to prove that our circuit and our Thevenin equivalent model will behave the same. Okay, so we want to prove that. So let me just choose a load resistor. So I'm going to copy this. All right, so this is our original circuit, and we have a Thevenin equivalent model. Now we just want to show that these two circuits will produce the same behavior or the same voltage current relation at the output. To keep things a little simple, I will choose a load resistance of 5 ohm. So let's say this is my load resistance 5 ohm, and I will connect 5 ohm to both circuits. And with this is 1 ohm. And now we can just calculate and see what do we get from the two circuits. Let's consider the Thevenin equivalent first. So from the Thevenin, I want to find the voltage across the load, VL, and I want to find the current I in the load, which is IL. Okay, so these two quantities I want to find in my Thevenin equivalent, and I will also like to find these two quantities in the original circuit. If these two are the same for both circuits, then this means the Thevenin equivalent circuit is a good representation of our entire circuit. Using the Thevenin, I can see that I have two resistors in series, 11 ohms and 5 ohms. So the total resistance is 16 ohms. Our total is 16 ohms over here. Therefore, the 8 volt supply will produce a current I. I will be equal to 8 volt divided by 16, and that is half an ampere. So 0.5 ampere will flow in this circuit. And because this I and this IL are the same, so I can say that my load current is half an ampere. When 0.5 ampere flows in this 5 ohm resistor, I can calculate the load voltage, which will be equal to 0.5 times 5, and that is 2.5 volt. So the load voltage is 2.5 volt according to our Thevenin, and the load current is half an ampere. These are the values that we can obtain from our Thevenin equivalent model, and you can see how quickly we can obtain these values. Now let's see if I want to find these two quantities using my original circuit. So if I'm solving in my original circuit this time, let's use nodal analysis. So I'm going to say that this is my reference node where the voltage is 0. I have one node V1 over here, and now I have a second node V2 because now we have a current that flows in this branch because it's not open anymore. So therefore I have two nodes, which will give me two equations, and then we will find the two voltages V1 and V2. Applying KCL at node 1, so KCL at 1, I know that the current entering the node must be equal to the current exiting the node. Therefore, I will have a current that is entering is 3VA minus V1 divided by 1 ohm plus 4 ampere is also entering is equal to the current that is leaving, and that is equal to V1 minus V2 divided by 4. Okay, so that's that. I have V1 and V2. These are the two unknowns that we want to have in our equation. We do not want any other unknowns. However, I have this unknown VA. And looking at the circuit, VA is equal to V2. You see V2 is the voltage from here to here. See, from here to here, that's the voltage drop, V2. And VA is the same. It is from the same point to the ground. So therefore, VA is equal to V2. So we can say that 3V2 minus V1 plus 4 equals V1 minus V2 divided by 4. So we just replaced VA because we want the equations to have only V1 and V2, the node voltages. Okay, now let's multiply by 4 on both sides. So we have 12V2 minus 4V1 plus 16 equals V1 minus V2. So this means I have negative 5V1 plus 13V2 equals to negative 16. Or we can say 5V1 minus 13V2 equals to 16. This is our first equation. The second equation can be obtained by applying KCL at node 2. So let's apply KCL to node 2. KCL at node 2, which says that the current in should be equal to the current out. Current in is the current that is flowing through the 4 ohm resistance, and the current out is the current flowing down through the 2 ohm and the current flowing through this 1 ohm and 5 ohm load. So we have these three branches, and I have assumed the current is coming in from the left and going out on the downwards and to the right. These directions are up to us. We can choose any directions. That does not change the final result. And we have discussed this in nodal analysis in one of our previous videos. So please watch that. Now let's apply KCL to node 2. The first current that is entering node 2 is coming through the 4 ohm resistance. So therefore we have V1 minus V2 divided by 4. So the current is V1 minus V2 divided by 4. That's the current that is coming in. It should be equal to the current that is going out. Current going out is V2 divided by 2 ohm resistance. So the current that goes through here to the ground. So it's V2 minus 0 divided by 2. So therefore we can write V2 divided by 2. And then another current that is leaving is V2 divided by the series combination of these two, which is 6 ohms. So V2 divided by 6. So we have V2 divided by 6. Now let's multiply by 24 on both sides. So we will have 6V1 minus 6V2 equals 12V2 plus 4V2. Now 6V1 is the only term, but V2 we have three different terms. So 12 plus 4 is 16, and 16 plus 6 is 22. So we have 22V2. Okay, therefore V1 is 22 divided by 6V2. This is our second equation. Let's put the value from second equation in equation 1. So we have 5V1 minus 13V2 equals 16. So we have 5V1, so this is V1, minus 13V2 equals to 16. This was our first equation. I just put the value of V1 from equation 2 into this equation. And now 22 divided by 6 times 5 is 18.33. So that's 18.33 V2 minus 13 V2 equals 16. So 18.33 minus 13 is 5.33 V2 equals 16. We can say V2 is equal to 16 divided by 5.33, and this is equal to 3 volts. So we found V2 to be equal to 3 volt. Now let's take a look at the circuit again. I have V2 equals to 3 ohms right now, 3 volt. Now 3 volt. Now we can use VDR here to find the voltage across the 5 ohm. We can do that. Or we can say that the current IL, we can find it using this 3 volts because the current IL is the same current that is flowing in this entire branch. And in this branch, we have a 6 ohm resistance, and the voltage drop from here to the ground is 3 volts. So therefore, the current will be, that will be IL. The current will be 3 volt divided by 6 ohms, and that is 0.5 ampere. This current, IL, is flowing in the load resistor 5 ohm. It's flowing over here. When this current flows in a 5 ohm resistor, it will produce a voltage drop of VL. So therefore, VL, the load voltage, would be IL times the 5 ohm resistance, which will be 0.5 times 5, which is 2.5 volts. Now you see the load voltage VL and the load current IL. They are the same that we obtained from our Thevenin equivalent. So this proves that our Thevenin equivalent is the correct representation of our complex circuit. And now we can appreciate that the Thevenin equivalent can simplify the circuit quite a bit. That's it for today. I hope you enjoyed the video. If so, please do subscribe. I'll see you next time, and bye for now.